Mr. Chairman, thank you for your kind introduction. Hello everyone, it's my great honor to give a lecture presentation at the 2022 IEEE Sensor Conference. I'm a PhD student from Southeast University and my name is Jian-Hua. Currently, I mainly focus on IF MEMS devices such as IF or microwave power frequency and phase detectors. The topic of my presentation is an expand microwave thermoelectric power detector in 0.18 micron CMOS technology. My presentation will consist of 4 parts as follows. First, some background information about this study. Second, the principal operation of the reported microwave power detectors and the corresponding electromagnetic thermoelectric simulation showed experimental results of the device. Finally, we come to several conclusions. Well-known IF microwave power devices are widely used in radio system, satellite communication, wireless mobile communication systems, and military fields. At present, the main IF power devices mainly include IF power amplifiers, low-noise amplifiers, and power detectors. Particularly in advanced IF transceivers, acute detector of microwave power is highly demanded. The power detector detects the transmitting power and takes the output through the couple and generates DC voltage output. This voltage is sent to a module which controls the gain of TX chain to optimize power consumption, improve linearity of the power amplifier, or control the gain of the transmitting and receiving chain. In the present work, we present an expand mean square microwave power detector based on dual heating using CMOS technology. The proposed detector mainly consists of 3 main components, namely a specific Cook-planar waveguide structure, 2 symmetric resistive loads, and many thermocouples. The principal operation of this device is to first convert all microwave power to Thermopile, which further converts Thermopile to DC output. In order to observe the microwave performance of the device more intuitively, we present the electromagnetic field distribution at an incident power level of 200 mW by ANSYS high-frequency structure simulator. When microwave power is fed into the CPW, the electric and magnetic fields are mainly concentrated on the 2 symmetrical microwave power absorbers. This indicates that the electromagnetic energy is well absorbed by the 2 symmetrical terminal resistor loads and converted into heat based on the Joule effect. Moreover, the corresponding thermal and voltage field distribution are also given at an incident power level of 200 mW by ANSYS. The temperature spreads out around the 2 terminal resistor loads, as can be observed. The micropower absorbers can reach a maximum temperature of 313.38 Kelvin. The results of the on-chip calibration and the measured return loss are also presented. A fluctuation of plus or minus 0.3 dB is observed after calibration. Moreover, the measured return loss is less than minus 20 dB in the operational bandwidth from 8 to 12 GHz. The result demonstrates the good impedance matching characteristic of the design power detector. Moreover, the measured output voltage versus incident powers is presented at 8, 10, and 12 GHz respectively. It can be observed. The output DC voltage and incident power show the here linearity, and the slopes are linear relationship between incident micro power and output DC are 3.82, 3.27, and 2.76 microvolts per milliwatt respectively. Furthermore, the measured resistance value of the Thermopile as a function of incident power is also given. It can be seen that the resistance value of the Thermopile and incident microwave power shares excellent linearity, and the measured slope are 1.24, 1.06, and 0.89 omega per milliwatt respectively. In summary, an expanded RMS microwave thermoelectric power detector based on jury heating in standard CMOS technology is presented, and the design stacing structure establishes a good linear relationship between micro power and DC voltage through many sensitivities. Thermocaps, the instant micro power directly establish an direct correspondence between microwave power and the resistance value of the Thermopile. The result through light on the development of the future heating-based microwave power detectors. Okay, that's the end of my presentation. Thank you for your attention.